The next subtopic will be 5.2, resistivity. Resistivity is different than resistance, but first I'm going to talk about resistivity first. So the current density J in a conductor depends on electric field and on properties of the conductor material. So we have already known that J is equivalent to I over A, which is also equal to N times Q times Vd. Now after doing some experiments and so on, scientists found that J is also proportional to E, where E is the electric field. If we increase electric field, then that means that J will also increase. So that is the meaning of this proportionality. So this is what we refer to as Ohm's law actually. I know that in school you have learned that Ohm's law is actually V equals to IR kan. This is Ohm's law, right? But in real physics lah, in fundamental physics, Ohm's law is actually this law. If we increase E, then J will also increase. So now let's do some mathematics to derive what is the resistivity from this Ohm's law. So we know that using mathematics, we can rewrite the proportionality using what we call as a proportionality constant, J equals to K times E. So this is the proportionality constant. So now I want to write this down as this one, 1 over rho times E. So now I want to introduce a value, a parameter, which I will call as rho. And this K is equivalent to 1 over rho. So now why I want to put this as 1 over, okay, let's talk about this for a while. If we have E electric as a constant, so now if E is constant, okay, now let's play around with the number of rho. If we reduce rho, if we reduce this number of rho, then J will actually increase. But if we increase the amount of rho, then J will decrease. So if you think about this for a while, if we increase the amount of rho, then J is decreasing. So rho is actually something that resists J. If we increase the resistance, then J will go down. So this is what is referred to as resistivity. Rho is what we call as resistivity. And then if we rewrite this in a more popular form, you will get as rho equals to E over J. So this is the definition of resistivity, and we get this from this proportionality constant. So rho equals E over J. The unit for resistivity is voltmeter over ampere or ohm meter. A perfect conductor would have zero resistivity, while a perfect insulator would have infinite resistivity. This table here shows the resistivities at room temperature or 20 degrees Celsius for conductors, semiconductor and insulator. Among conductors, silver has the lowest amount of resistivity, which is about 1.47 times 10 to the power of negative 8 ohm meter. So since it is 10 to the power of negative 8, this is about 0.000000147. So you get the idea. This is a very low value. Next lowest is copper, which is 1.72 times 10 to the power of negative 8 resistivity. So that's why we typically use copper in wires. And we also use aluminium in wires because both of them has a very low resistivity. Silver has the lowest, however silver is expensive, so that's why we still use copper and aluminium. And next is semiconductor. Semiconductor has a higher resistivity compared to conductors. For example, most of the conductors, all of the conductors have the 10 to the power of negative 8 resistivity. However, semiconductor has 10 to the power of negative 5 or maybe 10 to the power of negative 1. So this is very high compared to conductor. Next, finally, we have insulators. Insulators have very high amount of resistivity. For example, this is 5 times 10 to the power of 14. So this is 5 followed by 14, 0. So compared to this value, this is very extremely high. So metals have much lower resistivity than ceramics or polymers. So semiconductors are typically ceramic and insulators are typically polymers such as plastic. Silver and copper have the lowest resistivity among metals. Materials with constant resistivity is called an ohmic conductor. Resistivity usually is constant, so like this one, this is a constant number at a certain temperature and does not depend on electric field. So rho, I will call this as rho, is usually constant. However, it is only constant at certain temperature. So let's see what is the relation between rho and temperature. So the resistivity of a metallic conductor nearly always increase with increasing temperature. This is a graph showing the resistivity and the temperature for a metal. So if you can see, if we increase the temperature, the resistivity will also increase. So why does this happen? As temperature increase, the ions onto the conductor vibrates with greater amplitude. So we know that ion will vibrate inside any solid. So if they vibrate with greater amplitude, the ions will become bigger and bigger, making it easier for electrons to collide with an ion. This will decrease the velocity drift. And as you know, I is equal to NQVdA. So if velocity is going down, the current will also go down. So that means the resistivity will go up. So this equation here shows the relation between the resistivity and also the temperature. So in order for us to use this equation, you have to know two things. First, you have to know the resistivity rho naught at a certain temperature. This must be a known number. So rho naught is resistivity at reference temperature. This is what we call as reference temperature. Uh, Typically, reference temperature is used at 0 degrees Celsius or 20 degrees Celsius. So I have already given you the value for resistivity at 20 degrees Celsius in the slide before this. So if we know rho naught and T naught, we can actually calculate the resistivity at certain temperature. Maybe I want to know what will happen to my resistance when I increase the temperature to 100 degree Celsius. So now T naught will be 0 or 20 lah, 20 according to the table, and then T will be 100 degree. So rho naught you can already check from the table, and then you can finally use rho to find the new resistivity at 100 degree Celsius. Another way to express this equation is using this equation below this. This equation and this equation is actually the same. So we have another constant here, which is alpha. As alpha is called the temperature coefficient of resistivity, and it varies according to materials. So this is also a constant, which only depends on the material that is being used. So that's it for resistivity. Next, I'm going to talk about resistance.